This is a picture of an electrochemical cell. This is a piece of zinc here, which we are going to call an electrode. This is a piece of copper here, which is also an electrode. There is a wire connecting these electrodes. In this beaker, we have zinc nitrate, which, being aqueous, is really Zn2 plus ions and nitrate ions. And over here in this beaker, we have a solution of copper nitrate, which is really Cu2 plus ions and NO3 minus ions. This here is called the salt bridge. And in the salt bridge, we have something neutral, something that's not going to react with either of these solutions. Usually some sort of nitrate like KNO3 minus, something very, very unreactive. There's usually a little piece of cotton ball or steel wool or something there to keep it from leaking out. Over in this beaker, we have a reaction happening. Zn going to Zn2 plus 2 electrons. Over in this beaker, we also have a reaction going on. Cu2 plus 2 electrons goes to Cu metal. If you'll recall your redox chapter, this is an oxidation and this is a reduction. Because we've got this happening in two separate beakers, the electrons are going to flow from the zinc to the copper. In this direction, right like that. They're going to flow from here through this wire down here. That's the purpose of the salt bridge, to complete the circuit. Since these electrons are negative and they're flowing that way, the positive, the K plus of the salt bridge will also flow that way to kind of balance it out, and the negatives of the NO3 are going this way. The side where the oxidation takes place is called the anode of this cell. The side where the reduction takes place is called the cathode. The only way I ever remember that is the vowels are together and the consonants are together. That's my little mnemonic for remembering that. And if you think about what's happening in the cell, this zinc electrode will actually go away over time, get smaller as some of that solid zinc is turned into zinc ions. And this copper electrode will actually get thicker over time as more copper metal is being made from the copper 2 plus solution. And the blue color of this will fade away as the copper 2 plus ions go away. Now, you say to yourself, well, how do I know that it's the oxidation happening with the zinc and the reduction happening with the copper? How come it isn't the other way around? And the answer is, we can tell by looking at a table of potentials. Does this table look familiar? It's the table I've been giving out all through the year at every test, and we haven't used it yet. Well, now is the time to use it. This is a table of standard reduction potentials. So you will notice every single one of these reactions is a reduction. Now these are all measured values, and since we can't have a reduction without an oxidation, we need something to measure these against. If you look here at this one, that's 0. This is the standard electrode, the hydrogen electrode. It's the one everything is measured against. That's why it's 0. All of these things with a positive E, 0, E for at 0 up above stands for standard conditions, just like in the last chapter. But all of these positives, these are all better at being reduced than hydrogen. All these down here with the negative E reductions These are all better at being oxidized than the hydrogen electrode. So if we want to know how much electricity, how much voltage is going through that cell, we have to look at this table of potentials. So I look, now be very careful here because there are several possibilities for copper. I want this one, Cu2 plus 2 electrons goes to Cu solid. There's an E of 0.34. So the E reduction is 0.34 volts. Now I look and I see the zinc. There's the zinc one. That E reduction, standard, is negative 0.76 volts. Now if I'm figuring out the E cell, the E of this entire cell that I have on the other page, I can use those values. I can say Cu2 plus 2 electrons goes to Cu has an E reduction that's equal to, what did we say that was equal to? 0.34. And I've got the zinc. The Zn goes to Zn2 plus 2 electrons. Now that is not a reduction. That's an oxidation. So I can still take this value here, but I have to change the sign, because that negative 0.76 is for the reduction, and I'm talking about the oxidation. So now that's positive 0.76 volts. For the entire cell, I want to add those up. 6 and 4 is 10, carry 1, 1.10 volts. That's the voltage that is going through that electrochemical cell. You will note this is positive value, and if E cell is positive, that is a spontaneous reaction. This is called a galvanic cell. A galvanic cell happens spontaneously. You'll notice there's no battery or anything like that in the cell. There's nothing making this happen. This is happening all on its own. That's why it had to be in this direction. If I had said it was the copper oxidizing and the zinc being reduced, then my E cell would have been negative and it wouldn't have worked. So this is pretty standard. If you want to find the voltage of a cell, you look at this table, you find the two halves on the table. Both of them will be reductions because this is a table of reductions. Whichever one is being oxidized in your cell, and if they don't tell you, it's the one that's going to make the cell positive, you flip the reduction to an oxidation of whichever one you want, change the sign, and add them up. Now, this may be beginning to sound like Hess's law to you, and you're right, but there's actually a big, major difference between electrochemistry and state functions like Hess's law. These potentials are intrinsic properties, which means they don't depend on how much of the material you have. So if I have something like this gold one here with 3 electrons, E reduction for gold is 1.50 volts. Let's pair that one with the zinc. E oxidation for the zinc is again positive 0.76. But you'll notice the zinc has 2 electrons and the gold has 3 electrons. So if I wanted to write a balanced chemical equation, I'm going to have to write 3Zn plus 2Au3 plus goes to 2Au plus 3Zn2 plus. And there's going to be 6 electrons being transferred here. The 2 from the zinc times 3 moles of zinc. The 3 from the gold times 2 moles of gold. 6 electrons being transferred. But when I add these guys up, I don't multiply. I don't multiply that 0.76 times 3. I don't multiply this 2 times the 1.50. I just add them up. That's the difference between electrochemical and something like Hess. These are intrinsic values. You're still talking about 6 electrons being transferred. You still take into account these coefficients in that sense. But you don't do it when you add these up. Now, if you think about this, one application of all of these lovely redox potentials is an activity series. Remember the activity series where you had a single replacement reaction and you said something like, oh, this reaction isn't going to happen because you had like X plus My goes to XY plus M. And then you said, gee, X doesn't replace M, so there's no reaction. That whole activity series was created by looking at these electrode potentials, these reduction potentials. If the single replacement reaction gives you a negative E cell, it's not going to be spontaneous, then that reaction won't happen.